In section 4.1, you learned how to add, subtract, multiply, divide complex numbers, and to work effectively with powers and roots of complex numbers. It's helpful to rewrite them in a trigonometric form. So in section 4.4, we will be writing complex numbers in trigonometric form and using that to multiply and divide them. So I'm going to take a complex number in the form of a plus bi, and I'm going to plot it on this coordinate system where the horizontal axis is the real axis and the vertical is the imaginary axis. So my horizontal distance would be A, my vertical distance would be the B. So I have some point out here with coordinates A, B. And if I draw a little line segment here to connect the origin and my point, then we're going to call this angle. So from the horizontal axis to the line that I drew out to my point, we're going to call that theta, measuring it counterclockwise. So this distance is A, this is B. The distance from the origin to the point A, B, we are going to call R. And here's yet another application of the Pythagorean theorem. So this distance right here, it's just going to be the square root of A squared, which is this side, plus B squared, which is that distance. And so using R and theta, we can rewrite our coordinate A here as R times cosine of that theta, and our B would be R times sine of that theta. And R, I mentioned, was the square root of A squared plus B squared. Hopefully this is looking kind of familiar from way back in the beginning of the semester. But we're going to use this here to write the trigonometric form of complex numbers. So if we have this complex number A plus BI, the trigonometric form of this complex number would be R times cosine theta plus I times sine theta. Okay, so this is the trigonometric form of this complex number A plus BI. And so we find the R from the square root of A squared plus B squared. And one more handy bit of information that will help us with theta. If you look at my definitions here, hopefully you can see from that tangent, so if I did sine divided by cosine, is equivalent to B over A. To write the trigonometric form of a complex number, we need to find R and we need to find theta, and then we would just put it in this form in the box down here. So let's give that a try. So here we have a complex number, 1 minus the square root of 3i, and we're going to write it in trigonometric form. So it is in A plus BI form, and we can see that A is equal to 1, and B is negative square root of 3. And I need A and B to find R. R is equal to the square root of A squared plus B squared. So for this problem, that's the square root of 1 squared plus negative square root of 3 squared. And simplifying that, I've got the square root of 1 plus 3, which is the square root of 4, which is equal to 2. So R is equal to 2. The other piece of information that I need for the trigonometric form is theta. So I'm going to use the fact that tangent of theta equals B over A to try to figure out what theta is. So B over A for this problem would be negative square root of 3 over 1, which is just negative the square root of 3. So if tangent of some angle is negative square root of 3, what is the angle? So I'm going to figure that out. Maybe check on my unit circle, see where sine divided by cosine would give me negative a square root of 3. Another thing that helps me when I'm trying to find theta is to just roughly sketch a plot of this complex number. So on my real and imaginary axis, just to try to see what quadrant it would fall into, and that'll kind of help me see where theta should be. So if my real part is 1, I'm going to be coming over to the right, positive 1, and then I got a negative square root of 3 for my imaginary part, so that's going to put me down here in the 4th quadrant. So theta should be some angle that lands in the 4th quadrant. So I mentioned using the unit circle. You could also use an inverse if you did like arctan of negative square root of 3. And for this one, the angle that we're looking for is 5 pi over 3. So this tells us that theta has to be 5 pi over 3 because tangent of 5 pi over 3 is negative square root of 3. Okay, so now I've got r and I've got theta, so I can rewrite the angle and we call z. So I'm going to say z is my complex number in trigonometric form. And it's going to be r. Oh, let me write this first. We have this template, and we'll just fill in what we know. Okay, so it is equal to 2, our r is 2, cosine of 5 pi over 3 plus I sine of the same angle, 5 pi over 3. All right, so this is the trigonometric form of that complex number. Sometimes also called polar form. Okay, so here's another problem. We are going to rewrite the number 2 in trigonometric form. So we want to think about 2 as a complex number. And if I rewrite it as a plus bi, it would be 2 plus 0i. Is there the imaginary part is 0 because 2 is a real number. And so that'll show me a and b, and I can use them to find r. So r, the square root of a squared plus b squared. So for this problem, the square root of 2 squared plus 0 squared. Oops, squared. All right, so that's the square root of 4, which again is 2. And next we need to find theta. So theta, tangent of theta is b over a. And b is 0, and a is 2. So tangent of theta is going to be equal to 0. So I'm going to find an angle where tangent of that angle is 0, and tangent is sine over cosine. So for tangent to be 0, sine has to be 0. And also do a quick plot of this number. 2 is just a real number. So it'll be here, not going anywhere on the imaginary axis. So if I plot 2, it's right on my x-axis here. And that angle there is 0. So theta has to be equal to 0. Tangent of 0 is 0. So theta is equal to 0. All right, so I'm going to use r and theta to rewrite this in this form. So we've got 2 times cosine of 0, degrees or radians, plus I sine of 0. Right, and there's the trigonometric form of the number 2. Now let's see if we could go the other direction. If we are given the trigonometric form, can we write the standard form? And to do this, we could just evaluate. So evaluate cosine of 60 degrees and evaluate sine of 60 degrees and then add and multiply. Coordinates at 60 degrees, 1/2 and square root of 3 over 2. Remember the x is cosine and the y is sine. So cosine of 60 degrees is 1/2. And sine at 60 degrees is the square root of 3 over 2. Okay, so there I just evaluated sine and cosine. And here for this problem, I think I'm just going to go ahead and distribute the 2. And that's a little easier than trying to add here. But 2 times 1/2 is just 1. And 2 times this I times the square root of 3. 2 is going to cancel the 2 in the denominator. So I'm going to get the square root of 3 times I, or I times the square root of 3. And then I'm done. That is the standard form of this complex number. And if if I plot this, it should show up somewhere in the first quadrant, since 60 degrees is in the first quadrant. And that is what you would get, because you would go positive on the real axis and then positive on the imaginary axis, and that'll put you in the first quadrant. All right, now to multiply and divide them. We have kind of a little shortcut here, not real short, but a little bit of shortcut. Because if you think about, if you have these two complex numbers and you were trying to multiply them and you had to FOIL all of that out and combine like terms, you would end up with a lot of terms. And so if you did that and then you used a sum and difference formula, that would lead you to these two formulas that we have here. Here we've got a pattern that we have seen, that we see fairly frequently. If I'm multiplying, then I end up adding the angles. And if I'm dividing, then I end up subtracting the angles. I kind of remember the pattern of multiplication going with addition. Like with exponents, when you're multiplying, you add the exponents. When you're dividing, you subtract the exponents. Same with logarithms. When you're, expanding and condensing, multiplication becomes addition and division becomes subtraction. Something similar is happening here when we are multiplying and dividing complex numbers in their trigonometric form. So first we're going to multiply, and we're just going to leave the answer in trigonometric form. So we're not going to try to simplify it to a standard complex number. So this one, we're finding product and the formula for product. So let me write it here. So we're going to multiply the r's and then do cosine of our angles added together plus I times sine of the angles added together. Okay, so for this one, the r's are sitting on the outside here. So 2 times 6 is what we're going to do first. 2 times 6. And then we're going to have cosine of the sum of the two angles. So the angle in our first number is pi over 4. The angle in our second number is pi over 12. So we're going to end up adding those two together. And then we do I times sine of the same thing. Okay, so I'm going to go ahead and multiply the 2 times the 6. And now I'm going to add the angle. 12 is the common denominator. Pi over 4 is 3 over 12. So I'm adding 3 over 12 plus 1 over 12. So 3 pi over 12 plus 1 pi over 12 gives me 4 pi over 12, which will reduce to pi. And since the instructions tell us to leave it in trigonometric form, that is it. We will leave it just like this. This is the answer. Okay, so next let's do a division. And I will write that formula here. When we're dividing, we will divide our r's, and then we'll do cosine of the difference between the angles. So now we're subtracting. All right, so in our problem, our r's are 3 and 9. So 3 divided by 9 is just going to reduce that to 1 over 3. And then the two angles that we have are 50 degrees and 20 degrees. All right, simplifying that, I've got 1/3 times cosine of 30 degrees plus I times sine of 30 degrees. And this is in trigonometric form, so we're going to leave it just like that. All right, one more example. In this one, we've got a product of two complex numbers, and so we are going to rewrite both of them in their trigonometric forms and then multiply them that way, and then multiply them in standard form and make sure we get the same answer both ways. For part A, to rewrite, first do 2 plus 2r. To write it in trigonometric form, I need to identify this is B so that I can find R and I can find theta. So R is going to be the square root of A squared plus B squared. So the square root of 2 squared plus 2 squared. And that is going to be the square root of 8. And then our tangent of the angle is B over A. So tangent has to be 2 over 2. If tangent is equal to 1, then our angle would have to be pi over 4. So if tangent is 1, then sine and cosine are the same. and that happens at pi over 4. I know that I'm in the first quadrant because both A and B are positive, so I'm going to use pi over 4 for my angle, or 45 degrees. Okay, now I'm going to put it all together to write this in trigonometric form. So I'm going to put r first, so square root of A times cosine of pi over 4 plus I times sine of pi over 4. So there's the first number. So now let's do 1 minus I and write that in trigonometry. So A is 1 and B is negative 1. So I'm going to use that to get R. The square root of 1 squared plus negative 1 squared. So that's the square root of 2. And then I got to find theta. So tangent of theta is B over A. So 1 negative 1 over 1. We got to find the angle where tangent is negative 1. And of course, that happens at more than one place. So I'm going to think about where this angle should be. My real part is 1, so I'm going to the right positive direction. But then my imaginary part is negative, so I'm going to go down. So I'm going to end up here in the 4th quadrant. So I'm going to pick an angle in the 4th quadrant that has tangent equal to negative 1. And that one is 7 pi over 4. So this angle is 7 pi over 4. Putting all of that together, I've got the square root of 2 times cosine of 7 pi over 4 plus I times sine of 7 pi over 4. All right, so there's my two numbers in trigonometric form. That's part A. Now I'm going to multiply these two numbers in trigonometric form for part B. All right, so here are my two numbers that I found in part A, and I'm going to multiply them this way. So multiplying in trig form, I'm going to multiply the r's. So the square root of 8 times the square root of 2, which will be the square root of 16, and the square root of 16 is 4. So square root of 8 times the square root of 2 is 4. Yeah, let me take it back a step. I'll just write it. Square root of 8 times square root of 2. And then we have to do cosine. And for multiplication, we're going to add the angles. So we're adding pi over 4 plus 7 pi over 4. Okay, and then we're going to go through and simplify this. So on the outside, we get the square root of 16 or 4. Adding these together, they've already got the same denominator. So this would give 8 pi over 4, and 8 pi over 4 is 2 pi. All right, and this time we're going to simplify this further because in part C, we're going to multiply the standard form complex numbers, and the result of that is not going to have a sine and cosine. So to know if they're the same, we need to simplify this to a standard form. So we got to evaluate the cosine and the sine. So cosine of 2 pi is the same as cosine of 0, and it is 1. And then sine of 2 pi is 0. Okay, so simplifying that, I've got 4 times 1, which is just 4. So final answer here comes down to just 4. So in part C, I'm going to multiply 2 plus 2i times 1 minus I, and the answer should be 4. All right, so here we're just going to distribute or FOIL. So we're multiplying 2 times 1, 2 times negative I, and then 2i times 1, and 2i times negative I is a negative 2i squared. Okay, so our like terms in the middle here are going to cancel each other out. They add up to 0. And I'm going to rewrite the I squared as negative 1. So this becomes 2 plus 2, which is 4. So we do get the same answer both ways. Looking at that, it may appear that using the trigonometric form makes this problem longer, but it does become useful, like if you have to raise a complex number, like to the sixth power. Instead of multiplying it out 6 times, you can use the trigonometric form, and there's some theorems and patterns related to that.